Stop for a second. Look down. That dusty stone near your shoe probably looks completely ordinary, and most of the time it is. But every now and then, the ground hides something much stranger. Across the United States, people have found brown crystals shaped like natural crosses, feldspar that flashes with copper, sapphires that reveal moving stars, and clear quartz filled with golden needles. Some of these stones look unimpressive until you turn them toward the light. Others keep their most unusual feature hidden inside, and that's what makes them easy to miss. You don't need to believe every strange rock is valuable. You just need to know when something deserves a second look. Because these are 10 stones found in the United States that can make ordinary ground look very different once you know what you're looking for. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Number 1. The stone with a natural cross Staurolite. On a wooded trail in northern Georgia, there's plenty competing for your attention. Tree roots, loose gravel, red-brown soil, dry leaves. A small brown crystal probably isn't going to stop most hikers. But some Staurolite specimens have a shape that's difficult to forget. Two crystals intersect. From the right angle, they form something that looks remarkably like a cross. Nothing was carved into the stone. No one shaped it afterward. The form comes from crystal twinning. Essentially, two Staurolite crystals grow together according to a particular structural relationship. Depending on the way they intersect, the result can resemble a cross closely enough that people have been collecting these specimens for generations. They're often called fairy crosses. That name, of course, belongs more to folklore than mineralogy. People have associated the stones with protection, luck, and various local stories. Those traditions shouldn't be mistaken for geological evidence, but they do tell us something interesting about the way humans respond to unusual natural forms. Long before anyone could describe crystal lattices or metamorphic conditions, people still noticed that these stones look different. From a geological perspective, Staurolite generally forms in metamorphic rocks subjected to substantial heat and pressure. So the cross isn't really the remarkable part of the story by itself. It's the visible result of an ordered crystal structure formed deep within changing rock. Not every specimen looks clean and symmetrical either. Many crystals are damaged. Others intersect awkwardly. Some remain partly enclosed in the host rock. A sharply formed cross is much easier to recognize than a broken one, which means experience matters. Someone unfamiliar with Staurolite might see a rough brown object. Someone who has seen a few specimens before may recognize the geometry immediately, and that's a pattern we'll keep running into. The stone itself doesn't change. What changes is what the person looking at it knows. The next specimen makes that even clearer, because its most interesting feature may disappear the moment you turn it away from the light. Number 2. Copperlite inside, Feldspar, Oregon Sunstone. A rough piece of Feldspar isn't automatically impressive. Some Oregon Sunstone can appear pale yellow, clear, or only faintly colored when you first pick it up. Then you rotate it. For a moment, tiny metallic flashes seem to appear inside. Turn it back, and they may nearly vanish. Those flashes can be caused by very small copper inclusions within the feldspar. The effect is generally described as evanescence. In stronger examples, the copper can produce a glittering or reflective appearance that changes noticeably with viewing angle. This isn't quite the same as ordinary surface sparkle. The interesting part is within the stone. Oregon Sunstone can also occur in a surprisingly broad range of colors. Some material shows orange or reddish tones. Other specimens can display green, and certain stones combine more than one color. Still, rough material may give only a limited hint of what a finished stone could look like. That's where popular gemstone imagery can be misleading. We're used to seeing the final product: clean lighting, polished surfaces, carefully selected examples. The piece coming out of the ground may be dusty, fractured, or visually unimpressive. A person hoping to identify sunstone in the field would therefore be better served by understanding the geology and legal collecting locations than by simply looking for something bright. That's a useful distinction. Gem hunting isn't just spotting shiny objects. It's knowing what materials are plausible in a particular place. Once you know that copper-bearing feldspar occurs there, a brief internal flash suddenly means more. And with the next stone, light doesn't create a flash. It appears to draw a star. Number 3, the stone with a moving star sapphire. Not all sapphire is transparent. In fact, a rough or heavily included piece of corundum can look fairly dull compared with the faceted blue gems people usually imagine. Yet some of those inclusions can produce the very feature that makes the stone interesting. Under a concentrated light source, a bright star may appear across a properly cut surface. Move the stone, and the star seems to move with it. The effect is called asterism. It occurs when light reflects from large numbers of microscopic inclusions aligned along particular crystallographic directions. Usually the stone is cut as a cabochon, a smooth dome rather than a set of flat facets, to display the phenomenon effectively. That detail matters. A rough stone doesn't necessarily announce that it could become a strong star sapphire. The cutter has to understand the orientation of the material. Get that relationship wrong, and the star may end up weak, off-center, or barely visible. When everything lines up, though, the result can be striking. Some stars are soft and slightly hazy. Others show relatively sharp rays, and as the light moves, the intersection appears to glide over the dome. People sometimes describe this as a star trapped inside the gemstone. That's a nice image, although technically the star isn't sitting inside waiting to be released. It's an optical effect produced by light, inclusions, crystal orientation, and cutting. In a way, that explanation makes it more interesting. The phenomenon isn't simply an object, it's an interaction. Change the lighting or orientation, and the appearance changes too, which is why looking at a mineral from only one angle can be surprisingly limiting. Now compare that with the next stone. There, the lines don't appear because of an optical illusion. They're physically inside the crystal. Number 4, quartz with needles inside rutilated quartz. Imagine a reasonably clear piece of quartz. Inside are thin lines that may be yellow gold, brown, copper-toned, or reddish. Some cross at sharp angles. Others sit almost parallel. A dense cluster can resemble metallic hair, or, if you prefer the more dramatic comparison, lightning suspended inside glass. Those needles are rutile. Rutile is a titanium dioxide mineral, and under the right geological conditions, it can occur as inclusions within quartz. The visual result varies enormously. One specimen may contain only a few clean needles. Another can be crowded with them. And this raises a useful point about gemstone quality. People often hear that inclusions are defects. Sometimes they are undesirable, particularly when buyers value transparency and visual cleanliness. But that's not a universal rule. In rutilated quartz, the inclusions are usually the reason anyone is interested in the specimen in the first place. Without them, you'd simply have another piece of quartz. That doesn't mean every heavily included crystal is valuable or aesthetically appealing. Some are messy, damaged, or commercially unremarkable. Still, the broader principle holds. An inclusion isn't automatically a flaw. Mineralogically, inclusions can preserve evidence about the environment and sequence in which minerals formed. A later crystal may enclose an earlier one. Changes in temperature or fluid chemistry can leave physical traces. So those golden-looking needles aren't just decoration. They're part of the history of the specimen. Perhaps frozen lightning oversells it a little. But as a description of what a good piece looks like under directional light, it's understandable why the phrase sticks. The next stone is almost the opposite. You can rotate it under a lamp all day and still miss the feature people collect it for. To see that, you generally need a cross-section. Number 5, the stone with a hidden X, Chiastolite. At first glance, Chiastolite can seem fairly plain. Its exterior doesn't necessarily show a dramatic optical effect, bright metallic inclusion, or obvious cross. The pattern people recognize appears when the crystal is cut across its length. Then dark material inside can form an X or cross-like design. Chiastolite is a variety of andesite, and the darker areas are associated with carbonaceous inclusions concentrated during crystal growth. So strictly speaking, cutting doesn't create the pattern. It reveals its arrangement. That's worth distinguishing from Staurolite. Both can produce cross-like imagery, but for quite different reasons. With Staurolite, you're looking at two crystals growing together. With Chiastolite, you're seeing internal zones exposed by a cross-section. Visually similar, geologically unrelated mechanisms. Historically, that pattern attracted symbolic interpretations. including associations with protection and religious imagery. Again, those beliefs are better treated as cultural history than as claims about what the mineral actually does. But dismissing the folklore entirely would also lose part of the story. People noticed these patterns centuries before they could explain their mineralogical origin. The old interpretation and the modern explanation aren't competing descriptions of the same thing in quite the same way. One tells us about the crystal. The other tells us about the people who found it. And once stones begin producing forms that resemble familiar objects, our brains become very good at filling in the rest. That's especially obvious with the next two examples. They look like they contain plants. They don't. Number 6. A forest that isn't a forest moss agate. Hold a translucent piece of moss agate against a bright window, and you may see green, brown, or dark branching forms spreading through the stone. Some specimens look vaguely mossy. Others resemble underwater weeds or miniature shrubs. A particularly scenic piece can suggest a landscape surprisingly well. The natural temptation is to assume those patterns are fossil plants. They're not. Moss agate gets its appearance from mineral inclusions and growths within chalcedony. Depending on the material, iron or manganese-bearing minerals and other compounds may contribute to the branching or moss-like structures. Exactly which mineral produces a given color or pattern can vary, so broad descriptions are safer than pretending every green branch has one identical composition. What matters visually is that inorganic mineral growth can resemble organic forms very closely. Our brains help with the rest. Give us a few green branches and some translucent white space, and suddenly we're looking at a forest in fog. It's the same tendency that makes people find faces in clouds or animals in rock formations. The pattern is real. The landscape is our interpretation. That doesn't make it less interesting. If anything, it adds another layer. A small mineral specimen can become compelling, partly because geology created the structure and the human brain completed the picture. One piece may look like moss, another like a shoreline. Someone else might look at the exact same stone and see none of that. The next mineral pattern is less soft and ambiguous. Its branches can look almost unnervingly precise. Number 7, the stone that seems to draw trees, dendritic agate. There are dendritic stones that, at a glance, genuinely resemble botanical illustrations. A dark line becomes a trunk. It divides into smaller branches. Those branches divide again. The result can look remarkably like a leafless tree. Yet no tree was ever there. The dark features are dendritic mineral deposits, often involving manganese or iron oxides, growing along fractures or boundaries in the material. The word dendritic itself refers to a branching, tree-like form. What's more interesting than the resemblance, though, is how often branching geometry turns up elsewhere. Look at a drainage map. Small streams join larger ones. Look at roots exposed beside a washed-out trail, or lightning branching across a summer storm. The physical mechanisms differ, sometimes dramatically, but similar patterns keep appearing. That may suggest something broader about growth and transport in natural systems. When material or energy has to spread through space, branching can be an efficient outcome. We shouldn't push that comparison too far. A mineral dendrite isn't behaving like a tree in any biological sense. Still, the visual similarity is real enough that it can fool people, and perhaps that's why these stones are memorable. They don't merely look attractive, they look familiar in a way that seems slightly wrong. From branches we move to something much simpler, a metallic disc. And this time, the geological environment seems to have controlled the shape rather tightly. Number 8. Pyrite suns. Most people who know pyrite picture blocky metallic crystals, the classic fool's gold look. Pyrite suns from Illinois don't fit that expectation very well. They're flattened, often roughly circular. Crystalline growth radiates outward from the center, giving the specimen a sun-like appearance. A good example can look surprisingly manufactured, almost like a thin metal ornament pressed into shape. It wasn't. These specimens formed within sedimentary rocks, particularly in environments where available space restricted crystal growth. That restriction appears to have played an important role in creating the flattened form. And this is one of those cases where mineral identification alone doesn't tell the whole story. Knowing that something is pyrite explains its composition. It doesn't fully explain why this piece became a disc, while another pyrite crystal grew as a cube. For that, you have to look at the environment, What surrounded the mineral? How much room did it have? What fluids were moving through the sediment? What were the pressure and chemical conditions? Geologists may debate details of formation mechanisms in unusual structures, and simplified explanations can sometimes sound more certain than the evidence allows. Still, the broad lesson is solid. Crystal shape reflects not only chemistry, but also the conditions under which growth occurred. A pyrite sun is therefore more than a novelty. It's a physical trace of an unusual growth environment. Of course, if you found one loose without context, you might reasonably wonder whether it was natural at all, which is another reminder that context matters. Where did the specimen come from? What rock was it associated with? Does the geology of the location make sense? Those questions become even more useful with the next stone because its interior records several separate geological stages rather than one simple event. Number 9. The so-called dragon egg Septarian nodule. From the outside, a Septarian nodule can be underwhelming. Rounded, heavy, brownish or gray, perhaps crossed by a few cracks, then it gets cut. Inside, pale or honey-colored mineral fills can divide darker material into irregular sections. The pattern is why polished pieces are often sold under names such as dragonstone or dragon egg. Those names are memorable. They're also marketing language, not geological classifications. The actual story is more useful. Septarian nodules developed within sedimentary environments and later underwent cracking and mineral filling. The exact details can vary by deposit, and researchers have proposed different mechanisms for how some cracks developed. What we can say more safely is that the finished structure records multiple stages. Sediment accumulated, a concretion or nodule developed, cracks formed, mineral-bearing fluids entered available spaces, minerals, often including calcite, precipitated in those openings. So the dramatic pattern isn't a single event frozen in time. It's more like an edited geological record with several chapters preserved in one object. That helps explain why the exterior can tell you so little. The most visually distinctive features developed internally. Rock cutters know this uncertainty well. Before a saw opens a nodule, you may have clues about what type of material you're dealing with, but not the exact pattern inside. One specimen can be visually strong, the next may be rather ordinary. There's no guarantee. And that unpredictability is probably more interesting than pretending every nodule contains a perfect dragon egg. Our final stone has a different kind of history. Its bands formed in ancient volcanic rock, but ice later helped move the material around the Great Lakes region. Number 10. The stone carried by Ice Lake Superior Agate. Walk a gravel beach around Lake Superior, and most stones won't demand much attention. Then you notice one with a curved band, maybe red against white, perhaps orange, yellow, or brown. Wet the surface, and the pattern becomes easier to see. That may be a Lake Superior agate. These agates are associated with ancient volcanic rocks of the Lake Superior region. Long ago, volcanic processes left cavities in the rock. Silica-rich fluids later entered those spaces, and chalcedony accumulated in repeated layers. Those layers produced the familiar bands. Iron compounds contributed to many of the reddish and orange colors commonly associated with the material. But formation is only half the story. The agates didn't necessarily stay where they originally formed. Much later, glaciers moved across the region. Ice transported enormous amounts of rock, sometimes carrying material far from its original source. When the glaciers retreated, they left deposits behind. Since then, erosion, rivers, waves, road gravel operations, and ordinary weathering have continued to expose and redistribute stones. That means a small agate found on a beach may represent several very different geological episodes. Volcanic activity, silica deposition, glacial transport, modern erosion, all preserved in something small enough to sit in your palm. It's tempting to describe a stone like that as a traveler. Technically, of course, it didn't travel by choice, but the metaphor works surprisingly well. And unlike some exotic gemstones whose origins are thousands of miles away, Lake Superior agates remain closely tied to a landscape where ordinary people still search for them. You don't need to imagine a fictional treasure hunt. People really do walk those shorelines looking down. Which brings us back to where we started. So next time you're walking beside a river, crossing a trail, or standing on a rocky shoreline, look down for a second. Most stones will be ordinary, but every now and then one may carry a pattern, crystal structure, or geological story that isn't obvious at first glance. That's the real lesson here. You don't have to assume every strange rock is valuable. You just have to know when something deserves a closer look. Because nature doesn't put labels on what it creates. And sometimes the difference between an ordinary stone and a remarkable discovery is simply the person who stopped long enough to notice it.